This short video lecture introduces the Coriolis effect or Coriolis effect, geostrophic wind and jet streams, the Earth's atmospheric circulation, and the ocean conveyor belt circulation. To explain Earth's atmospheric circulation, we first need to take account of the so-called Coriolis effect. As an analog for the Coriolis effect at the northern hemisphere, we will use a merry-go-round-like disk that rotates in an anti-clockwise fashion when observed from above. You are sitting near the outer edge and your friend is sitting near the center of the disk. You are both firmly attached and facing each other. You are both asked to roll a tennis ball over the disk's smooth surface in each other's direction. Observed from where you sit, your ball curves to the right. Observed from where your friend sits, your friend's ball also curves to the right. Why is this? You are sitting near the outer edge, so both you and the ball experience a high velocity. Your friend near the center experiences a lower velocity. Your ball rolls inwards over parts of the disk with slower velocities. The ball, however, carries its original faster velocity with it, and from where you sit, you see your ball curve to the right. Now think from your friend's perspective. Your friend's ball rolls over parts of the disk with increasingly faster velocities. Your friend's ball also carries its original but now slow velocity with it. Your friend sees the ball also curve to the right. Actually, you may sit anywhere on the rotating disk and roll the ball in any direction. Viewed from wherever you are sitting on the disk, your ball will always curve to the right. For instance, when you sit midway the disk's radius, facing the center, and roll the ball to your right, you add the ball's velocity to the disk's velocity, causing the ball to deflect to an area of higher velocity, which is to the right of the ball's path of motion. If you had rolled the ball to your left, you would subtract from the disk's velocity, causing the ball to deflect to an area of lower velocity, which again is to the right of the ball's path of motion. Now replace the rotating disk with Earth's northern hemisphere and the rolling ball with a moving air parcel, and you can easily imagine that an Earth observer who studies the path of an air parcel in the northern hemisphere observes a similar effect, a curved deflection to the right. Actually, watching from a stationary position in space, an observer would not see the air parcel deflect, but rather would see the air parcel moving in a straight line with the Earth rotating out from under it. To an Earth observer, the curved deflection on the southern hemisphere, which has a clockwise rotation when viewed from under the South Pole, is to the left. At the Earth's equator, where both hemispheres meet, the deflection is zero, with the deflection increasing towards the poles. At the poles, the deflection is at the maximum and the perfect spin against the rotation of the Earth itself. The mechanism leading to curved deflections of moving air parcels over our planet Earth is known as the Coriolis effect and is named after the French scientist Gaspard Gustave de Coriolis, a fanatic billiard player who physically described the movement of billiard balls on a rotating billiard table in 1835. The mechanism itself was first identified in 1778 by Pierre-Simon Laplace. The Coriolis effect is related to the Earth's rotation, one rotation per day, and acts on relatively long-lived phenomena such as mid-latitude cyclones and large vortices in the ocean. In contrast, the water that drains from your kitchen sink or bathtub rotates every few seconds and flows fast. Contrary to what some people may want to make you believe, the Coriolis effect is much too weak to determine the direction in which water drains from your kitchen sink or bathtub. This picture shows the situation at an altitude of around 9 to 10 km. The picture is a plan view from above. Higher up in the atmosphere, the air movement experiences little friction. Generally, air moves in the direction of a location with lower energy. Because we are regarding air movement here at the same altitude level, this means that air moves to a location with lower pressure. Here we have an isobar of 512 millibar, which is 512 hectopascal, and here we have an isobar of 500 millibar, 500 hectopascal. Air moves in this direction due to the pressure gradient force. As soon as the air starts to move, the Coriolis effect comes into action. On the northern hemisphere, this causes a deflection of the air movement to the right. This deflection to the right continues with the air movement as shown here until an equilibrium state is reached where air movement is parallel to the isobars and where the pressure gradient force and the Coriolis effect are counteracting each other, are balancing each other out. Wind blowing parallel to the isobars is called a geostrophic wind. You can experience its force when you fly in an airplane from west to east. The geostrophic wind then acts as a tailwind and will make your journey quicker than if you were to fly in the opposite direction, thus from east to west. We know geostrophic winds blowing horizontally through the upper layers of the troposphere from west to east, but with its flow shifting to the north and south as jet streams. These jet streams are at an altitude of approximately 8 to 15 km, some 6 km wide, and meander over a width of 200 to 800 km. Actually, there are two jet streams in the northern hemisphere, a polar jet stream and a subtropical jet stream, and likewise two in the southern hemisphere. Jet streams typically follow the boundaries between warm and cold air, as we can see in the next picture. This picture shows the atmospheric circulation on the northern hemisphere in cross-section view. Here we have the equator, here we have the North Pole. The Earth receives much heat at the equator and very little at the poles. This causes transport of heat in the direction of the poles and of cold air in the direction of the equator. Because of the Earth's rotation, the Coriolis effect, and also the uneven distribution of land masses and oceans, a number of global circulation cells are created. The Hadley cell, named after the English lawyer and amateur meteorologist George Hadley, Ferrel cell, named after the American meteorologist William Ferrel, and the polar cell. At the equator, warm air rises and starts to flow in the direction of the poles at an altitude of around 15 km. At latitudes of about 30 degrees, the air descends. In the northern hemisphere, this descending air is responsible for deserts such as the Sahara and the buildup of the semi-permanent Azores anticyclone. This figure shows the descending air splitting at the Earth's surface. Some of it flows back to the equator, whilst another part continues to flow towards the poles. Meanwhile, at the poles, cold air sinks and is transported over the Earth's surface in the direction of the equator. In the mid-latitudes, around 60 degrees, cold air from the poles and warmer air that has continued its routes towards the poles meet, as shown in this picture. When cold and warm air masses meet, frontal precipitation is formed. At the equator, we have rising air as a result of heating of the air at the Earth's surface, which can lead to convective precipitation. The picture also shows the positioning of the polar and subtropical jet streams perpendicular to this cross-section. This picture shows the same circulation patterns, but now in three-dimensional view. Here we have the equator, winds in the direction of the equator on the northern hemisphere with a curved deflection to the right, and on the southern hemisphere with a curved deflection to the left. Here we have the mid-latitudes, the area with westerly winds, and here typically the area where cold polar air meets warmer air from the south. What is also important with regards to the distribution of heat over the Earth, and thus for the climate, is what's happening in the oceans. This picture shows the ocean conveyor belt circulation, where you have cold, deep currents, which are indicated in blue, and warm, shallow currents that are indicated in red. Warm ocean water travels from Florida in the direction of northwest Europe. On its journey, the warm ocean water becomes more saline due to evaporation. Direct cooling of this saline water by air south of Spitsbergen further increases the density of the water, causing it to become heavier than the water below it and to sink to greater depths, from where it's carried as a deep, cold return flow southwards to the tropics again. Because of the Gulf Stream and North Atlantic drift, winters in Western Europe are mild, especially when compared to the winters at the same latitude in Western Canada and Alaska.